Now, I already pointed out that it's pretty useful to consider spaces. And you have to be reasonably creative in the spaces you consider. So in this field of collaborative filtering, which we're going to be discussing, we have two, in the simplest case, we have two things, two types of things. So we have users and we have items. And the users are say, the customers at Amazon, and the items are the things Amazon sells. And let's suppose we have n items and m users. So one way of thinking of this problem is in a space which has dimension n. So remember, this is a space which has coordinates. We have one coordinate for every item, and we have the number of points in the space is equal to the number of users. And then every user is represented by a vector in the space, where that vector has a component for every item. Now, this is not a very sensible space by classic criterion. There is not really a vector space because essentially for all users, you only know the components of that vector for the items the user knows about. And those, as I pointed out earlier, were sparse. So this is a case where the only vectors, the points, are not really solidly located in this space, because we only know the coordinates in this space for a few of the items. And there is a technology called the Pearson coefficient, which allows you to find the distance in this space. The simplest normal formula doesn't work because the normal formula assumes that you know what those coordinates, what the vector component is in every dimension. We definitely do not. There's a tiny fraction of items is known, say Amazon items are known to any one user. And in the Pearson coefficient, when you have two users, these are 2 points in the space, you only look at those items which each user knows about. And as far as Amazon is concerned, that is typically that each user ranked or clicked on that particular item. Actually, you can look at this problem in an alternative way. This is the difference in user-based and item-based analyses. And in the item-based, we think of the items as the points, and the space has dimension m when there are m users. So this is the sort of dual of the previous way of looking at it. And now every item is represented by a vector in user space. And again, the components of that vector are the ratings of the particular user, because every user member is a dimension in that space. Again, this is very sparse. A given item is only going to be rated by a few of the users, although some items are actually rated by a lot of the users. This is a feature of the long tail, remember. But there's actually the long tail, which is the items which are not ranked by many people, which are possibly the most important, because the common ones are pretty easy to deal with. And here, the so-called cosine measure is a distance measure that can be used. And that only sums over users that rate both two items. Now, we're usually taught spaces and vectors, and we add the vectors, and we look at scalar products and stuff like that. But this doesn't work here. We have points, we have spaces, and some of our intuition is correct for those points and spaces. But some features are not really. The intuition breaks down because you can't take scalar products in general, because most of these vectors are sparse, and you just don't know the components, so you can't take a real scalar product. However, in most of the analysis, all you want is a distance. Although technically, when we actually look at the algorithms are actually easier to write down when they're real vectors. But there aren't real vectors. You just have points in a space. That's very important, because the intuition of points living in a space is a good intuition. And then we have distances, which measure how close those points are in those spaces. When we have people in an item space, those people are similar if they rank items in a similar fashion. Um, and items are similar in that space for one or two reasons. Either you look at the content of the item, like the music genome, and find those items have similar content, or you look at there actually is a more serious space where of a more classic take. For the music genome, you have various uh, ways you're ranking a song, you're um, classifying a song, and you could possibly have every song classified by essentially all possible categories. But when we're looking at the user view, every song is only going to be rated by a few users. But we can still define distance. I mentioned Pearson and cosine. And if we look at distance between points, there are two properties which are nearly always true. And these are useful properties. First is that distance is always positive, 0 or positive. And the other is that the distance between A and B is the same as the distance between B and A. If they're not, you'd actually take the average of what your naive estimate was, and then you call that the distance, and then that will actually give you this symmetry property. There's another property of distances which is well known called the triangle inequality. This inequality is rarely true in these obscure spaces which aren't really vector spaces. Now, the basic recommender algorithms are actually built around some simple ideas such as nearest neighbor. That's why I said the concept of a space is interesting. We have intuition about space. Things that are near each other are meant to be similar. So collaborative filtering is essentially a nearest neighbor algorithm. You find the points that are near each other, and there are two versions of collaborative filtering depending on whether you do it in the item space or the user space. Another important approach, which is also we have intuition for, and that is to divide the space into regions. We're always thinking of spaces divided into regions. Those regions are things like so-called latent factors or topics, and they're equivalent to the regions in spaces we're familiar with. And there we use the technology called clustering or Gaussian mixture models, latent semantic analysis, latent Dirichlet allocation. All of these methods correspond to dividing space into regions. And those dividing space into regions is one of these offline ideas, because you cannot do that online. Although once you've got it into regions, if a new item comes along or a new person comes along, you can decide which cluster they belong to very quickly. So we will do clustering a little more detail later on. And these particular pictures here of clusters are completely irrelevant, completely inapplicable, because they correspond to pictures in a real space. But I pointed out we don't have real spaces. We don't actually have points because we're missing most of the components. But still, the intuition and actually the algorithms are not so different between the clustering in real spaces and clustering in these obscure spaces. There's a famous 2003 article from Amazon on the recommender system, and they point out that clustering can be done offline, but not online. But you can, as I say, classify users. If you have already determined a set of clusters, which is a set of regions, you can actually assign a new user to one of those regions very fast. That's not obviously the best way. It's just one of the methods that are used, and it is not necessarily the best method.